Parallel tangents to a secant. Welcome, everyone. Today, we are going to dive into a very interesting geometric relationship titled parallel tangents to a secant. Before we begin our main exploration, let's quickly refresh our memory on two fundamental terms we've covered in our previous lessons. First, recall that we defined a secant as a straight line that cuts through a circle, intersecting it at exactly two distinct points. On the other hand, we know that a tangent is a special kind of line that just barely grots a circle, touching it at exactly one single point. In this lesson, we aren't just looking at these lines in isolation. Instead, we are going to explore the dynamic relationship between them. We will be analyzing what happens to the nature of the line as we take a secant and move it parallel to itself, shifting its position relative to the circle. Let's see how this movement transforms a secant into a tangent. Understanding the concept. Now that we've refreshed our definitions of secants and tangents, let's move into the heart of today's lesson. To truly understand the relationship between these two types of lines, I want you to perform a conceptual experiment with me. First, picture a circle on a piece of paper, with its center labeled as capital O now. Draw a secant line that cuts through this circle, intersecting the edge at two distinct points, which we will call point P and point Q. If you look closely at the part of the line that lies inside the circle, the segment from P to Q, you'll recognize this as a chord of the circle. Now, here is the crucial part of our experiment. I want you to imagine shifting this line, PQ, in a direction that is perpendicular to itself. As you slide it, make sure you keep the line perfectly parallel to its original position, moving it steadily away from the center, O. Keep this movement in mind, because in the next few slides, we are going to analyze exactly what happens to that chord as the line approaches the edge of the circle. Step-by-step analysis of the movement. Now, let's begin our step-by-step analysis by looking at what we call Step 1, the initial state. To start our experiment, imagine we have a secant line passing directly through our circle. As we discussed in the previous slides, a secant is defined by its ability to intersect the circle at two distinct points. In this specific case, let's label those two intersection points as P and Q. At this starting position, the line is positioned relatively close to the center, which we've labeled as O. This means the distance from the center O to our line is quite small, creating a relatively long chord between P and Q. Keep this image in your mind, because in the next step, we are going to begin moving this line away from the center. Step-by-step analysis of the movement continued. Now that we have established our starting point with the initial secant line in Step 1, let's move on to Step 2, where we begin the actual movement. Imagine we are now shifting that line, PQ, so that it moves parallel to its original position, but specifically in a direction that carries it further away from the center, point O. As we perform this shift, you'll notice that the line is still cutting through the circle, meaning it continues to intersect the circle at two distinct points. However, pay close attention to the segment between those 2 points, the chord. As the line moves closer to the edge of the circle and further from the center, the length of this chord begins to decrease. This observation is crucial, as it sets the stage for what happens when we reach the very edge of the circle in the next step. Step-by-step analysis of the movement continued. Now, let's move on to Step 3, where we look at what happens when we reach the limit. Remember, in the previous step, we saw that as we shifted the line away from the center, the chord was getting shorter. As we continue this movement further and further from the center, you'll notice that those two intersection points, P and Q, are actually moving closer and closer together. Eventually, we reach a critical moment where the distance between them vanishes and the 2 points coincide, merging into a single, solitary point. At this exact position, the line's behavior changes fundamentally. It no longer cuts through the interior of the circle, but instead, it merely touches the edge. This brings us to our next step, where we will formally define this new state as a tangent. Step-by-step analysis of the movement continued. Now let's look at step 4, which marks the critical transition to a tangent. Up until this point, we've been watching our line move further away from the center, causing those two intersection points to get closer and closer together. But once we reach that precise moment where the line touches the circle at exactly one single point, a fundamental change occurs. The line no longer cuts through the interior of the circle. It ceases to be a secant and officially becomes a tangent. This is the limiting case we've been approaching throughout our analysis. Step-by-step analysis of the movement continued. Now, we have explored what happens when we move the secant line away from the center in one direction, but we shouldn't stop there. To complete our analysis, let's look at step 5, which is the symmetry on the opposite side. Think back to our starting point with the original secant line, passing through points P and Q now. Instead of moving the line further away from the center in the direction we just studied, I want you to repeat this exact same process, but in the opposite direction. Move the line across the center of the circle toward the other side. As you shift the line this way, you will notice the same pattern occurring. The length of the chord, the segment between the two intersection points, will begin to decrease. Just as we saw before, this continues until the line eventually reaches a point where it touches the circle at exactly one single point, but this time, it happens on the opposite side of the circle. This brings us to our conclusion, where we will see that there are actually two such parallel tangents in total. Conclusion. Based on the step-by-step movement we observed in the previous slides, we can now state a fundamental rule. For any given secant line, which we've labeled as PQ, there are exactly two lines parallel to it that act as tangents to the circle. As we saw when we moved the line away from the center in one direction, and then repeated that process on the opposite side in step 5, these two tangents are always positioned symmetrically, one on each side of the center. So, let's bring everything we've just analyzed together to reach our final conclusion. To help you visualize this more clearly in a practical sense, let's look at a real-world example in the next slide. Real-world example, the sliding ruler. Now, to make sure this concept is crystal clear, let's step away from abstract diagrams and look at a real-world visualization. Imagine you have a circular coin sitting on a table, and you place a ruler across it so that the ruler cuts through the coin at two distinct points. In this first step, the ruler is acting exactly like the secant line we've been discussing. It's intersecting the circle at 2 points. Now, for step 2, I want you to imagine slowly sliding that ruler away from the center of the coin. The key here is to keep the ruler perfectly parallel to its original position. Don't rotate it, just slide it. As you perform step 3, pay close attention to the part of the ruler that is actually overlapping the coin. You'll notice that as the ruler moves further from the center, the length of the chord, the part of the ruler covering the coin, becomes shorter and shorter. This leads us to step 4. Eventually, the ruler will reach a point where it no longer cuts through the coin, but instead, it just barely touches the very edge of the coin. At this precise moment, the ruler has transitioned from a secant to a tangent. Finally, in step 5, if you continue sliding the ruler all the way across to the opposite side of the coin and repeat that same movement, you will find a second, identical position where the ruler touches the edge. This perfectly demonstrates our conclusion from the previous slides, that for any given secant, there are exactly two parallel tangents, located on opposite sides of the circle. With this visual in mind, let's move on to summarize the key takeaways from today's lesson. Key takeaways. First, let's look at chord length. Remember our step-by-step analysis where we shifted the line away from the center? We observed that as a line stays parallel to our original secant but moves further away from the center of the circle, the length of the chord, that segment between the two intersection points, gets smaller and smaller. Second, we have the concept of the limiting case. This is a crucial mathematical idea. We saw that as the two intersection points move closer together, they eventually meet. Therefore, we can say that a tangent is simply the limiting case of a secant, occurring at the exact moment those 2 points merge into one single point of contact. Third, regarding existence. For any secant line you can possibly draw through a circle, there will always be exactly 2 lines parallel to it that act as tangents. And finally, let's note their position. Because a circle is perfectly symmetric, these 2 parallel tangents won't be on the same side, they will be located on opposite sides of the circle. All right, let's bring everything we've discussed today together. We've walked through the movement of a secant line, and now it's time to summarize the key takeaways from this lesson. Now, before we wrap up, I want to point out a few common mistakes to watch out for in your exams, specifically regarding how we define these lines and how we identify their positions. Common mistakes. First, be careful not to confuse secants and tangents. It sounds simple, but remember the fundamental definition we discussed at the very beginning. A secant must intersect the circle at exactly 2 distinct points. If that line moves so far that it only touches the circle at one single point, it has officially ceased to be a secant and has transformed into a tangent. Don't let that distinction slip in your proofs. Second, watch out for the assumption that there is only one parallel tangent. When we were analyzing the movement of the line, we saw that as we shifted the line away from the center, we reached a tangent on one side. But don't forget the symmetry of the circle. As we noted in our conclusion, if you move the line in the opposite direction, you will inevitably find a second, corresponding tangent on the opposite side of the center. There are always exactly 2. Finally, make sure you don't misunderstand the concept of parallel in this context. When we talk about shifting the line to find these tangents, we are moving the line in a direction perpendicular to itself. This ensures the line stays parallel to its original position. If the line rotates or changes its angle as it moves, you are no longer performing a parallel shift, and the relationship we've studied today will no longer apply. Keep these distinctions in mind, and you'll master this concept easily. Now, before we wrap up today's lesson, I want to pause and address some common pitfalls. As we've seen throughout this presentation, the transition from a secant to a tangent is a subtle but crucial distinction, and it's easy to get tripped up.